Okay, well, you got a homework assignment due today. And it sounds like there might be a question or two. So, what have we got here?
So on 1423A.
On 1423A, that was to prove the, is that to prove 1423?
Yeah.
Yeah, it's to prove 1423A, right. So that is, let's take a look at it up here. So that's rho times the quantity sigma union theta equals rho times sigma union rho times theta. So that's distributivity. That's a distributivity law.
Now, do we need to use an arbitrary ordered pair for that one?
Exactly. That's exactly what you have to do. So because this is an equality between two sets, we use the technique we use to use two sets equal is with a 9.8 limit. But now the question is this: it's an arbitrary ordered pair. So what I recommend you do is you say let BD be an arbitrary.
BD this time?
Well, that's what I recommend. But I mean the letters that you use are immaterial, right?
Yeah.
But so for 14.23, 14.23a, proof, start off by let BD be an arbitrary ordered pair, ... You can go on from there, right? And do what? And prove what?
That ordered pair is an element of both sides.
Yeah, that arbitrary ordered pair is an element of this equals that arbitrary ordered pair is an element of this. And then start with the left-hand side. And then once you get that, then you'll know what it is because you'll be able to use an arbitrary ordered pair for the definition of multiplication, right? Because I think the definition of multiplication was
You were just about to definition product.
yes, definition. So now you can use this form here, and this will be there exists a C, right? So there exists a C, but now it's going to be complicated here because you got a pair, you know.
It's with sigma replaced by.
Will be there exists a C. Yeah, and this will be in here this will be the rho, but with sigma replaced by that parentheses.
Sigma theta,
Yeah, that parentheses. Yeah. Okay. And then what you'll have is in that parentheses. Then what you'll have is there's a union in there, right?
Yeah.
So then the question is, what does it mean to have
A union of two.
yeah, what does it mean to have an element to be an element of the union? So you have to use the what? The
1120.
yeah, whatever the union is, right? You go back and I think it's
1120.
Yeah, it's 1120 axiom union. Wow, you remembered that number? This guy actually remembers that 1120 was axiom union. I don't know. I can't remember that. That's why we had the equation sheet. Yeah. Okay. And then I think you'll have to use and distributes over or, and I think you just crank it out. You know, I think it's pretty. I mean, once you get to that point, it's just cranking it out. Yeah, there's only one way to do it. You know, after you get that.
And then how about 14, 19E?
Right. That is rho inverse is a subset of sigma inverse, right? 1419E here. Let's go. Oh, here it is. It's up here. 1419E. Prove that rho is a subset of sigma equivals rho inverse is a subset of sigma. Okay. So I would just start with the right hand side this time. Okay. And use what?
I couldn't figure it out.
Well, it's a subset, right?
Yeah.
There's only one thing to do. Go back and figure and go look at what it
back to subset.
to subset. Well, yeah. I mean, what else is there? right? So go back and look up, so what is it, what is the one for subset? What is the definition of subset? Oh, now you're gonna, now, okay, so we'll have a little office pool to see if you can remember what the number is for
Yeah, what's the
subset.
number? Property.
What is the
Property, 14.
subset? 13. Right?
Oh, I didn't go back that far.
Yeah, see up here, look, here it is, 11, 13 subset. But now, remember though, with this subset, this is an ordered pair, so this X is XY, you know.
So we need X, Y as an element of.
Yeah, ordered pair X, Y.
It's,
Yes, ordered, yeah. Right?
yeah, for all X, yeah, it's, this is
all
good,
X,
for all,
Y,
for all XY
ordered pair X, Y.
is an element, exactly. So you have to use the ordered pair version of that. That was a good question. But you see how to do that. This X, you know, the elements are ordered pairs, and this X in the definition of subset is really can stand for a list of variables, you know, in this case X, Y. So are we good?
Good.
Those are good questions. But I think with that in mind, it's, you know, it's pretty straightforward.
Was there an exercise too?
There was. And you know what you had to do, I think it was 1418. And I think what you needed to do with that is just do some products. You know, it gives you, the exercise gives you a row and it gives you a sigma, and it asks you to compute the product, rho times sigma, and asks you to compute the product sigma times rho. So you just have to do the, you know, the way to do that is to do the, you know, if there's one from here to here and here to here. You know how we did the, you know how we did those diagrams the other day? We had,
Right. Yeah.
you know, this one to this one, this one to this one, and the product is if there's one from the first one to the third one.
Okay.
If there exists a C in the middle, or you can just do it by hand. I mean, you can just look at it and you could kind of trace through. I always like to do it visually. I always kind of like to draw a picture. But
The product is just
if there exists a C in the middle.
No?
Well, you have, for example, on the first one,
Right.
is the ordered pair BB in the product?
No.
Correct, it is not. Because there does not exist a C in the middle, right?
Right.
Okay, but is BC in the product?
Yes.
Yes, because there exists a what? The B in the middle, right?
Okay.
Okay, so anyway, it's, and then powers, okay? Are we good? All right. Today, then, we are going to do big topic. Now, I have, here. So here's what we're doing. We are doing properties, or classes of relations. Now, I have something to say about table 14.1. So let's take a look at table 14.1 in your equation sheet. Here we have A, B, C, D, E, F. We have 6 different definitions. All right? Now, these definitions are really important. In fact, these definitions are so important that I'm going to tell you right now one of the questions that's going to be on the next test. It will be, you need to memorize. Every once in a while, I ask you to memorize something, okay? This is one thing that you have to know, that you just have to commit to memory. All right? You need to memorize the first 2 columns of table 14.1. And here's how I'm going to, and so what we have here is the name, let's take a look at the first one. The name reflexive and the property for all B, B rho B. That's what it means to be reflexive. These are all definitions, by the way. The first 2 columns are just definitions. Okay? So reflexive means for all B, B rho B. Irreflexive means for all B, not B rho B. Okay, these are properties that...
So let's memorize one of them and the other one kind of follows.
Yeah, and then symmetric, what does it mean to be symmetric? It means for all B and C, for all B and C, B row C equals C row B. Actually, we know some of these already. We've done symmetry before, you know. But this is the formal definition, okay? Anti-symmetric means for all BC, B row C and C row B implies B equals C. Asymmetric is for all BC, B row C implies not C row B. And transitive means, we've done transitive before, for all BCD, range true, if B row C and C row D, then B row D. So I mean, you know, we've actually talked about some of these properties before, so it shouldn't be that difficult. But here's how I'm going to ask the question on the exam. What I'm going to do is, because this is in the equation sheet, and you have an equation sheet, I mean, I can't just ask you to say, you know,
You can.
I can't just say, don't look at the equation sheet and write down the definition. So what I'm going to do is I'm going to have, the very first question of the test is going to be, you know, some of these. And and without the equation sheet, you'll do the first page, okay? You'll give me the page, and then you'll get the equation sheet and do the rest of the exam. So that's how we're going to do it. So just to let you know that this is coming up, these are so important that you have to know what these properties are. All right?
Okay.
So that's the deal. Now, what we're going to do now is we need to explore what these are. Now, let me tell you then that the name and the property, those are definitions. Now, on the third column, we have what's called alternative. So this alternative means these are alternative definitions. And even though the name and the property are definitions, it's a theorem. We actually have 6 different theorems here. It's a theorem that the alternative equivales the property. Do you see what I mean? So these are actually 6 different, in this table we have 6 definitions and 6 theorems. The 6 definitions are the name with the property, and and we will. What we'll do, we'll prove one of these. You have a couple of them for homework, okay? But before we do that, so that's the relationship between what is an axiom and what is a theorem according to this table. Now, but before we go and jump into some proofs, I think it would be helpful for us to take a look at an example and run through each one of these, because one of the things that another exercise that you have in your homework is to identify whether a relation satisfies a particular property. You see what I mean? So here's what let's do. Let's consider the less than relation on Z. So this is table 14.1. And consider the less than relation on Z.
Don't we not put parentheses around 14.1 because it's not
It is, well, it is a table. Well, whatever. Okay.
You're always the one that's...
Yeah. You're right. Yeah, actually, my notes do not have a paren. So, okay. On Z, and by the way, when we say on Z, we really mean what?
Z cross.
Yeah, Z cross Z. You know. Okay. Now, and what I want us to do is let's determine whether the less than has each one of these properties. Okay, just one at a time. Okay, so we'll start off with property A. Reflexive. Now, what is reflexive saying? Reflexive says that for all B, B row B. Now, is it the case? Oh, I said less than. I meant greater than. Sorry. Okay, so let's consider this relation. So here the relation is row. Here is a specific relation greater than, right? So is this true? B is greater than B. For all B, is that true? Is it true that for all B, B is greater than B? What? No. So therefore, greater than is not reflexive. Are you with me? So what's part B? How about irreflexive? Is it true that for all B, it's not the case that B is greater than B? Is that true? That is true. So what we're saying then is that the greater than relation is irreflexive. You see how you determine these properties? Okay, let's see if it's symmetric. Okay, is it true that for all B and C, B is greater than C equivales C is greater than B? Is that true? No. So it is. That means it's not symmetric, right? In other words, if B is 5 and C is 7, this would be false, but this would be true, right? And false doesn't equal true. Are you with me? Okay, let's do another. Let's do the next one. Now the next one is a little tricky. Anti-symmetric. Well, it's here. It's not symmetric, but I wonder if it's anti-symmetric.
Question: is it always either reflexive or irreflexive?
Oh, that's a good question.
Or anti-symmetric?
Yeah, that is a very good question, and I'm going to let you think about that.
Yes.
Yeah, I'm going to let, yeah, because, and furthermore, what about symmetric? If it's not symmetric, is it anti-symmetric? I mean, because there's also an asymmetric. So, I mean, yeah, that's a really good question. That's a nice thing to think about as you encounter these definitions. And you should think, you know, not just not, yeah, you should be thinking. It helps the gray matter, you know, it helps the synapses in the neurons get connected. Okay, so D. Okay, so how about anti-symmetric? So what does it mean? What would anti-symmetry? In other words, if we have B is greater than C, and C is greater than B, does that imply B equals C? Now this is tricky. This is a really.
It's always false. You can't have B is greater than C and C is greater than B.
But this is not saying B is greater than C. It says B is greater than C and C is greater, implies B equals C.
Because false implies true.
True, because false implies anything is always true. Okay, so this is a bit tricky, yeah. Yes, because the antecedent is always false. That's a weird. We will say weird on this. I mean, okay. Okay, but so here, yes, because antecedent is always false.
Which means the whole thing
Is always true. Yeah, it is kind of weird. I agree. This one's weird. I agree. But mathematically, there's no argument, right? Okay. Now, how about E? How about asymmetric? Now, how about asymmetric? Now, asymmetric says for all B and C, B row C implies not C row B. So here we would say, is it true that B is greater than C implies not C is greater than B? Is that the case for the less than relation? If B is greater than C, does that imply not C is greater than B?
No.
Yes.
We have a difference of opinion here. We have to break the tie. What do you think? Yeah,
Oh,
see, the
yeah.
majority
C
wins.
and C cannot be greater than B.
Yeah. Okay, so this is yes. So here, this one was yes, this one is yes. Yeah? Are we good? And how about transitive? F.
Greater than C and C. Yeah.
Yes.
Yeah, this one's yes. So we have B is greater than C, and C is greater than D implies B is greater than D. That one's a yes. So you see, any given relation could have this property or not, and you need to be able to go through. Let's do one that's not quite so usual. One that one that you probably haven't considered before. So consider the relation. Consider the relation B square C.
All right.
B square C on Z. Now, what do we mean by that? What we mean by that is square square is the set of ordered pairs. It's going to be the set of ordered pairs 0, 0, 1, 1, 2, 4, 3, 9, ... Does everybody see what that relation is? I'm just making up a relation just called square just to illustrate whether it has these properties or not. Now, what about A? Is it true that for all B, B row B? In other words, is it reflexive? Is this property reflexive?
Square? No.
Square. Is it reflexive? Yes or no?
9.
Why not?
Because the third element in that set.
Yeah, there's no 2, 2. No, wait. It's not because there is a 2, 4. It's because there's not a what? Not a 2, 2. Yeah, now is that, are you with me on that? No, there is not. There's also not a 3, 3. There is a 0, 0 and a 1, 1, but it has to be for all.
So those
Are you with me?
Those are all B's?
Yes.
Yeah. Is everybody clear on this? I mean, oh, this 0, 0, maybe it is reflexive. Oh, 1, 1, maybe it is reflexive. Ah, shoot, it has to be for all.
Right.
I mean, for all B. There's no 2, 2. There is...
What's the 2, 2 hiding somewhere in that dot?
Well, there's not. There is hiding in the dot. There is no 2, 2 or 3, 3.
There's no 2, 3 in the dot. Well, there's got to be something over there.
There's no, All right. Now, how about B? Is it, oh, hey, it's reflexive. I wonder if it's irreflexive.
No.
Wait a minute. You mean it's not reflexive or irreflexive either?
I was wrong.
What does irreflexive say? For all B what? Not
But there is
B row B. Yeah, okay, so this is also no, yeah? Because it does have 1, 1. Does have 1, 1. All right? So here again, you must memorize the property and the name and the property from table 14.1. Those are you just have to know what those are.
We're done with this.
Now, there's, no, we're going to prove. Now, and like I said before, there's an alternative definition. And what we are claiming is that, let's take, for example, A, the reflexive property. What this table is claiming is that for all B, range true, B row of B, equivales I sub B is a subset of rho.
Aren't you basically saying that I sub B is a subset of rho equivales true?
No, we're saying it equivales for all B, B row B. We're saying that the property equivales the alternative.
That property is true, isn't it?
No, it depends on the relation.
Oh, right.
It depends on for some relations are reflexive, some are not.
Right.
Yeah, now that's a good point.
Well, because you said there was definitions.
Right, but these are properties.
They equivalent to a definition. That would be saying equivalent to true.
Well, the point of it is that some is that
I'm getting that, right?
well, some relations are reflexive, some are not. Some are irreflexive, some are not.
All right.
Okay, but what is equivalent? I mean, so we can't say that this is true. This is true for reflexive ones, for reflexive relations. Okay, that's all right. So now for actually, I'm asking you to do B, C, and D. B, C, and D are homework assignments for next time, and so you'll have to prove. So let's do A, because that's not assigned. Okay, so proof. So proof of table 14.1. No, sorry. No parentheses. No parentheses. Table 14.1. proof of table 14.1a that the property equals that property equals alternative. That property equivales alternative. Okay, so what we must prove is, what it is that we're asking is for all B range true, B row B, for all B range true, B row B equivales, I sub B is a subset of row. I sub B is a subset of row. Now, how do you think we should start here?
Start with the right-hand side.
Yeah, the right-hand side or the left-hand side?
Right-hand.
Yeah, you guys are getting good at this. Because the right-hand side, we can go the definition of I sub B, we can do the definition of subset, you know, and with a subset, hopefully we'll try to work our way to this. Okay, so I sub B is a subset of row. Is a subset of row equals by what? Yes, 1113. 1113, which is the axiom subset, right? Okay, so what is...
Roll X, Y.
Yeah, but now you're right. This is ordered pairs. So we got to do the ordered pair version. Is everybody clear on that? If you look at... Okay, so this is for all x, y, range what?
Range ordered pair X, Y is now I sub B.
Range ordered pair x, y is an element of I sub b. Okay? Body.
Ordered pair X, Y.
Good. Ordered pair x, y is an element of row. Whoa, is this slick? Is this slick or is this slick? You can just go right back to these definitions, la-di-da, la-di-da. And what do we have? What, does this look familiar?
Yeah.
Does this look familiar?
Identity lemma.
Yeah, this is the identity lemma. Okay, so this equals by the identity lemma, which is what? 14.15.3. Oh!
Dang.
Identity lemma. And what does it mean for this? If xy is an element of I sub b, what does that make? X equals y. Ha! For all xy, range x equals y, xy is an element of row. Oops, xy is a row. And now 1 point rule and textual substitution, right? So what was the 1 point rule?
Can we do it even though we have two dummies? Yeah.
Oh, wait, actually, we should, no. Yeah, good point.
We can't 1 point rule? No. Or it's just not good?
Because normally the 1 point rule.
Yeah, you're right. Yeah, you're right. We were jumping ahead. Yeah. So what do we want?
Well, we gotta get rid of that.
Trading?
Yeah, I think nesting, right? You want to look that up?
Yeah. It's crazy.
You guys got... Because what we want is, we want to be able to...
Yeah, and we know
To get
that
this
X
to-
equals Y is the same as X equals Y and if I for all X.
Okay, hold on. So let's give the...
Pulling a rabbit on this one.
Well, I don't know. I don't think so. This is, what did you say it was? 8 point what?
20.
8.20 nesting?
Yeah.
Well, with 820, what are the ranges? Why don't we just do the ranges? With what?
It's the range is and key.
Okay, so let's say 8.25 nesting with RQ. If you want to do this, with RQ replaced by what?
Something X equals Y and true.
Yeah, but I think we want the true.
You want true and?
I think we want the X equals Y in this one.
Yeah.
Are you with me?
Yeah.
So I think we want this to be true X equals Y. Am I right?
Yeah.
Okay.
And yeah, it's 339.
True X equals Y. Yeah? So this will be what? For all X, range what?
X equals Y. For all x range true.
range true,
For all y.
and then for all y. Are we good on this? Is everybody calm?
Pretty much, yeah.
Okay, and then for all y, range x equals y,
Blah, 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 blah.
xy is an element of rho. Okay?
One rule.
Is this good? Because here the true, you know, yeah?
1 point rule. You could have done it the other way around anyway.
Well, whatever.
Yeah.
Yeah, you're probably right.
Take that.
Okay, so now this will be 1 point rule. What, do you have a number for that?
14.
814?
Yes.
8.14, 1 point rule.
And textual substitution.
Yeah, let's just combine. We've done this, so, right?
All x range true.
And so this will be,
Y, y.
so this is for all x range true. So now the dummy is the y, right?
Yeah.
Oops, I forgot.
Do we want x replaced by y?
Well, that's the good, see, the dummy is y, so everywhere there's a y, we replace it by x instead of the other way around. Are you with me? Is everybody clear on that on the 1 point rule? The y,
You have to take whatever the dummy.
you have to take whatever the dummy is.
And then we're done.
I mean, you know that x equals y is the same as y equals
Then we
x.
rename. And then we're done.
Yeah, we won't even bother renaming because we know. Okay, so y, so everywhere there is everywhere there's a y, we replace it with x. So we have x is an element of rho. So this is for all x range true. X is an element of rho. Boom.
Very close. That's it.
Sure. I mean, dummy renaming.
Technically. It doesn't look the same.
Well, come on.
it's not like
BB. Yeah, it is dummy renaming.
Notation.
It's it's dummy renaming. Oh, you're right. We have a notation thing. Oh, yeah. Sorry. Yeah. No, 14.15.4
Is XX
equals, sorry. 14.15.4 notation. Yeah, sorry about that. And then what? For all x range true. And now what is this? X row x. Boom. And now, dummy renaming.
So we had to do that whole proof on. Was it dummy renaming or change of dummy?
No, I
And we
don't.
never used it.
Is it dummy renaming or change of dummy? No, it's dummy renaming, right?
Yeah, but
Think
dummy
Jane-
name was the stupid proof.
So we had to memorize it, but we're never going to use it.
No, that was the change of dummy, wasn't it?
Yeah, that's what I was after.
Same day, they're all annoying.
Okay, now, so you see, it's the same kind of approach to do B, C, and D for the homework, right? Now, isn't this great? Man, at this point, I think it is so neat that all of that stuff that we did before, all of that stuff about subsets and the quantification and it all, we have all those tools and we can just build on it and to learn about relations. This is the neatest structure.
And we're going to keep
This is the
using
neatest,
later.
well, you will forever, for the rest of your life.
Does it ever conclude to something? Greater knowledge.
Okay.
Welcome to school.
Okay. Now, next next topic, the last topic for today is the topic of closure. All right?
Right.
So, and let me start off by saying that there are 3 closures. There are 3 closures. Okay? Here, and each one of them has a name, obviously. The first one is reflexive closure.
Symmetric and transitive.
Ha. Reflexive closure. The second one is symmetric closure. And the third one is transitive closure. Now, the definition of closure is, so that's the fact that there's 3 of them and those are their names. But now, let's take a look here at 14.30 in the equation sheet. Because, and let me just say that what our author could have done is he could have had a definition of reflexive closure and defined that. And then he could have had a definition of symmetric closure with another axiom and defined that. And then he could have had a third one with transitive closure with another axiom and defined that. But instead, he combined all three of them into one definition. So look at his style here. He says, let rho be a relation on a set. The reflexive, parentheses, symmetric transitive, closure of rho is the relation rho prime that satisfies blah, blah, blah. Now, yeah, so let me explain what this, how to read this. So first of all, let's just forget about the parentheses, okay? Forget about the parentheses. The definition says, let rho be a relation on a set. The reflexive closure of rho is the relation rho prime that satisfies rho prime is reflexive. B, rho is a subset of rho prime. C, if rho double prime is reflexive and rho is less than or equal to rho double prime, then rho prime is a subset of rho double prime. Okay. In other words, everywhere. Okay, so that's the definition of reflexive closure. Now, the definition of symmetric program is the exact same words, only everywhere we said reflexive that time, you say symmetric. And then the definition of transitive closure is the exact same thing, only everywhere where we said reflexive or symmetric, now you say transitive. Okay, because so you didn't want to have to repeat that 3 with just the change of the names, right? Yeah. So this is an abbreviation for really three definitions, these three kinds of closures. Is everybody clear? That's how to read that. Okay? Are we good? Now, what the heck is the concept of closure? What does all this stuff mean? Okay? It means this. I'm going to give you an example of reflexive closure. Example of reflexive closure. Okay, now let's take this. Let's suppose that we have the set B, and it's 0, 1, 2. All right? And let's take our old friend, the less than relation. And the less than relation is what? What is the less than relation over B cross B, where B is 0, 1, 2? What is the less than relation?
0, 1.
0, 1.
2.
0, 1. 0, 2. 1, 2. Is everybody good on that? Now, I have a question for you. Is this reflexive? Yes or no? Is it reflexive? You remember what reflexive means? Let's go back and remember what is reflexive.
No. It means that they're all equal.
It means that for all B, B rho B.
The identity of B is a subset of relation.
Yeah. And it's not. Okay, so now here's what we mean by closure. Whenever you close a relation, what you do is you keep all the original ordered pairs and you add just enough ordered pairs to make it be reflexive. So you kind of like close it. You make it reflexive. But now obviously you could add, well, but the trick is you only want to add just enough ordered pairs to make it reflexive and no more. You see what I mean?
So we turn less than into less than or equal to.
Well, actually, that's what will happen. The reflexive closure of less than will be less than or equal to. But I want you to understand. I want to try to get you to understand how this ABC stuff works. Okay, so look. So what this says is that the reflexive closure of rho is the relation rho prime that satisfies. So here's my question. Let's denote less than prime. Less than prime is the reflexive closure of less than. Now let's see what properties it has to have. First of all, rho, this has to be reflexive. Yeah? Okay, so what must we have? So we must have the following three things. Do them A, B, C, just like they are up there, A, B, C. We must have less than prime is reflexive. Are you with me? And then what does B say? What does B say? Yeah, so in this case, what would it be? Less than is a subset of less than prime, right? Now, what does that mean? That means that whatever less than prime is,
Had the original elements.
it's got to have the original elements. Yeah. Are you with me?
Yes, sir.
Now, if it was just A and B, if it were just, oh, well, actually, let's do C. Let's write out what C means. No, yeah, but let's write out what C is. What does C say? If what? Let's write out C in this example. What does C say? If what?
Less than double prime.
If less than double prime is what?
Reflexive.
Is reflexive. And what? And what? Double prime, yes, and yeah, good. Okay, yeah, less than is a subset of less than double prime. Then what? Less than prime is a subset of less than double prime.
Does that limit the unit?
This part C is what limits it to be not adding any more than you need to add to make it reflexive. So let me see what A and B says. A and B say that we must add ordered pairs to less than to make less than prime reflexive. Are you with me? So A and B say that we must add ordered pairs to less than to make less than prime be reflexive. Are you with me? So that tells us right away that we must add what? That right away, well, which ones? So so according to A and B, so we know we must add what? So tell me the ordered pairs.
0, 0.
So we must add 0, 0, 1, 1, 2, 2. Okay? But now, if there were no C, are you with me here? If there were no part C to the definition, we could add more. We could add more.
So part C limits us.
Yeah. Let's just pick one. Let's just say 1, 0, okay? 1, 0. And so we would have this. We would have this. Let me just make up a name. Sigma would be the set of ordered pairs, the original one, 0, 1, 0, 2, 0, 3, okay? And then these three that we add
Isn't it 1, 2?
are
Yeah.
0, 1, 0, 2, oh, 1, 2, sorry. Oh, yeah, 1, 2. That was the original. Yeah. 1, 2, okay. And then these three, 0, 0, 1, 1, and 2, 2. And then this extra one, 1, 0. Let's just define this, 1, 0. Now, do you see this satisfies A and B, right? Okay, so sigma satisfies A and B. But what about C? So C does not allow sigma to be the reflexive closure. However, C does not allow sigma to be the reflexive closure. Because why? Because what is the reflexive closure? Because less than prime equals what? Now what is x? What is x? What is this? 0, 1, 0, 2, 1, 2, 0, 0, 1, 1, 2, 2, right? It satisfies this, but we don't have what? But we don't have what? Sigma is a subset of less than prime. That's why sigma cannot be the reflexive closure. You add just enough to make it reflexive, but no more. See, you add just enough to make it reflexive. And no more. So it seems like it's kind of a strange way to do it with these prime. First you have rho, then you got rho prime, then you got rho double prime, okay? But that's the only way that you can say it mathematically. This is the way to say that mathematically. You see what I mean? If rho double prime is reflexive, any reflexive one, I mean, it could be the universe and it would be reflexive, right? If double prime is reflexive and rho is a subset of double prime, the original one is this, then the true reflexive closure has to be a subset of that. See, so that's what makes the rho prime be as small as possible. You see that? You see the reasoning there? Well, see, this is why I wanted to do an example with, this. We wouldn't have this because there would exist one. You wouldn't have this in C. This is why sigma. This is why sigma cannot be the reflexive closure because it doesn't satisfy C because we don't have this is less than or equal to this.
Isn't that kind of like assuming conjunct? This and this and this.
Well, it is an implication. He could have written this. He could have abbreviated this and said rho prime is reflexive and rho is a subset of rho implies, yeah. Okay, good deal. Have a great spring break.